Hello, folks. So we are back. I am back. Um, we have got done talking about a little bit of special relativity and a little bit of the beginnings of quantum physics. And we learned about photons, namely that light can be described with waves. Um, and we had Young's double slit experiment, which was like very good evidence that light behaves like a wave. But then, right around 1900 or so, it was realized that a sort of wave packet or corpuscular nature of photons of light was required in order to explain some things like the black body spectrum. And right, so it was Planck and then later Einstein who realized that what we had to do was think about photons with a particular energy. The subscript gamma is oftentimes reserved for for light or photons. So this is given by basically the Planck-Einstein formula, h times the frequency of the light. We also realized, because of Einstein's theory of relativity, that the energy of a particle is related to its momentum and its mass. But since the photon doesn't have a mass, the photon energy can also be written in terms of its momentum times the speed of light. In other words, you learn that, yeah, in fact, the photon does have momentum, even though it has no mass. Okay, and I guess one more thing to remember is that the speed of a wave, or in this case a particle, is related to its wavelength times its frequency. And if you're interested in light, then that the relevant speed there is c. So these are sort of the three fundamental equations for doing that early quantum mechanical stuff. And you can start putting things together to just solve for the momentum of a photon if you wanted. So apparently from this equation, it follows that the photon has a momentum equal to the energy divided by c, right? Energy divided by c. Well, the energy over there is h over f. So this is h over f over c. And if you think about it, f divided by c is the same thing as 1 over lambda. So in fact, that got inserted at this juncture. And then finally, that's true. So this turns into h over lambda. If you're not sure why that's true, just pause the video and make sure the algebra works out. You'll notice the speed of light vanishes, and the energy of the momentum of a photon is simply related to h over lambda. So that was sort of known around, let's say, 1905. It took some time, and in the intervening years, right, the interesting discrete atomic spectra of a number of atoms was observed, and someone like Niels Bohr was able to come up with some kind of explanation of it. But then the really concrete explanation of why, for example, atomic spectra only have these certain colors, which I'll show you a picture soon, really came down to understanding something called wave mechanics, and the sort of more modern word for that is quantum mechanics. So it all kind of starts here, realizing that a photon has a momentum equal to h over lambda. So it was, I think, Louis de Broglie, or de Broglie, or something, however you want to say it, a French guy, I believe, or he might have been Belgian, who knows. It was his sort of wild idea to say, okay, and this is interesting. So a particle, or rather a wave, with a wavelength can have, on some level, a momentum. A wave can be made to come in a kind of packet, and that packet has momentum. Can the logic go the other way? Do things that have momentum necessarily have a kind of wavelength? Do they have a wave-like nature? Is it possible that all things that have momentum also have a wavelength or a wave description? So that's the story. So we'll just say de Broglie had the wild idea to basically say perhaps momentum of any particle is related to the Planck constant divided by lambda. So that seems kind of wild, right? That would even mean that even particles like protons and neutrons and electrons could somehow have a kind of wavelength. What would it mean if matter as we know it, like we think of it like billiard balls bouncing around, what would it mean if they could have a wave-like nature? That is what we'll get into. But first, let's, I guess, do a calculation. So suppose that this is true, that everything that has momentum has a wavelength. So I'll say for all particles. This is a guess, but it turns out it's experimentally verified. So let's suppose, as an example, that there's an electron, could be a proton, it doesn't matter. An electron goes through a potential difference. That is to say, an electric potential difference, delta, let's call it delta V, which is has a magnitude of 71 volts. And it goes from, it's picking up energy as it does this. It starts from rest and does that. So after it travels through the 71 volt difference of electric potential, I'd like to know if this formula is true, the de Broglie formula is true, what is the wavelength of the electron? And sounds a bit complicated, but so the idea is if we're going to use this formula here, we will need to solve for the momentum. Okay, if we're going to solve for the momentum of an electron, how could we do that? Well, it might help if we can figure out how fast it's going, and perhaps even more straightforwardly if we can figure out what its kinetic energy is. Why is that relevant? So let's see. First of all, the kinetic energy that the electron is going to pick up will be equal to the potential energy that's lost, and that will be given by the charge of the electron times the change in potential. In other words, that is simply the charge of the electron times the 71 volts, and so in many ways it's going to have 71 electron volts of kinetic energy. How do we relate kinetic energy with momentum? Well, you could use it to solve for the speed and then multiply by the mass, but maybe a more straightforward way to do it is to think of it more like this. The kinetic energy is given by 1/2 mv squared. V is velocity, not the V for volt, sorry. I am totally free to write this as mv quantity squared divided by 2m. You can verify that one of the m's cancel and you get back what you're supposed to. That's kind of convenient because it allows me to write this as the momentum of the electron squared, or the momentum of any particle, divided by 2m. That's a nice trick, being able to write the kinetic energy in terms of the momentum. So that we will need to set equal to 71 electron volts. Yeah. Okay, so let's do that. I think the way that I'm going to solve this is I'm going to convert the 71 electron volts to joules, and I'll do that in a moment. So I'm going to solve for P. P is square root of 2m times 71 electron volts. And remember, P is h over lambda. So then you can solve for lambda simply by multiplying it by both sides. In other words, h over square root of 2m times 71 electron volts would be the wavelength. Now I'm going to write 71 electron volts. That is equal to, remember the way that this works out, an electron volt is simply the charge of the electron times a volt. So I can multiply, or I can just say that this is equal to 71. The electron charge is 1.6 times 10 to the minus 19 coulombs. Coulombs times volts, but a coulomb times a volt is the same thing as a joule. So we will do that. So that is 1.14 times 10 to the minus 17 joules. The mass of the electron is 9.1 times 10 to the minus 31 kilograms. And H is approximately 6.63 times 10 to the minus 34 joules times seconds. So, if we plug everything in, what I find is that this is about 1.45, maybe 1.5 times 10 to the 10 times 10 to the minus 10 meters would be the de Broglie wavelength of that electron. Okay, so we used a formula. We were able to calculate the wavelength of a particle with a particular momentum, with a particular energy. Okay, so what? If this is actually going to be true, if particles can have a kind of wave-like nature, then we should be able to test that, right? We should be able to see matter behaving like a wave, which is odd. I've never seen anything like that with my own eyes. But we can make a prediction and we can see what will happen. So this might be the kind of thing you're interested to do. We just got done talking about the wave nature of light and what happens when you send light through, two slits and you get this interference pattern because light's a wave. Yeah, cool. All right, well, if you sent electrons through two slits, what would you expect to happen? Now, if you're not the kind of person that watches a lot of PBS science specials, you probably have an intuition for what you would expect to see. You might want to think about it for a moment, but I'm going to tell you what I would think. So I would think there's no reason in the world to not expect, with a beam of electrons coming through, that you'd expect, a pattern of electrons like over here and a pattern of electrons over there. Maybe it's not going to be so clean, maybe there's actually going to be a lot of scatter, but you expect to see a lot of them here and then they kind of space out, and then a lot of them here and then weaker. You just don't expect to see many in any other place. But if matter in some way behaves like a wave, then you wouldn't expect to see this. You'd expect to see a kind of interference pattern. And that's exactly what is seen. This image is showing the result of hitting a photographic plate with a beam of electrons after they have passed through two slits. You'll see as these slides develop, A, B, all the way through E, more and more electrons are allowed to pass through one electron at a time. And you'll notice that by the time you get to E, there's a very distinct pattern there. There are many maxima and minima, indicating that that this pattern really is the result of what you'd get when you have wave-like behavior. So it really is true that under the right careful conditions, matter can behave like a wave, and it can also behave like a particle.